Now, okay, so is it? So topic 5 for SL is all about enthalpy and heat content of a system. And so the first thing you kind of want to establish is what enthalpy is, okay? So enthalpy is defined as the heat content of a system, okay? So I guess to kind of make it simple, imagine if you took all of the energy that was contained in the molecule and converted it into heat. That's what the heat content of the system is, whether it's potential energy, kinetic energy, whatever. It was converted to heat. That's how much energy you would have. Enthalpy is signified by the letter H, okay? And so every system has a certain amount of enthalpy stored inside it. Now, we don't care about individual systems of enthalpy. What we care about, bless you, is the delta H, okay, which is the change in enthalpy of a reaction, okay? So what we care about is how much heat energy changes from the reactants to the products of a reaction. That's our big idea here. Okay, so we care about delta H. We don't necessarily care about H, we care about delta H. Okay. And you'll notice that there are other kind of subscripts and superscripts that will attach to this term. If we have delta H with a degree symbol up top, that means standard enthalpy of reaction. Okay. There's some subscripts that you might see as well. You might see delta HF with the degree symbol. Sorry, that's an F down there, which is standard enthalpy of formation, which we'll talk about a little bit later when we start talking about ways to calculate enthalpies of reaction. And you might also see delta HC, which is standard enthalpy of combustion. Those are the big kind of delta H values that you may have to calculate or use to calculate in this topic. Okay, so yes, Marina. Yes, correct. So really in all of chemistry, if you see a little degree symbol as a superscript, that means standard conditions. Yes. And so standard for thermodynamics is 25 degrees Celsius or 298 Kelvin and 100 kilopascals. It's different for gases, but for thermodynamics or energetics, those are your standard conditions for a reaction. Okay. So everything we learn about in this unit is techniques to measure the difference in change of the enthalpy between the reactants and the products. And when we calculate that value, there's two possibilities for that value to represent a type of reaction, okay? And so you will either have, this is kind of going to be a table, a 3-column table, so you kind of see this. You can either have an endothermic process or an exothermic process.
You said 3 columns.
Yeah, the middle one's gonna be like the topics. So like this will be like description. So the middle one will have like categories, and then we'll talk about how they relate to endothermic and exothermic. And there's a lot of things kind of going down here. It's not a lot of lines, but it's a lot of writing for comparisons. This is kind of one of those compare contrast things where endothermic and exothermic have a lot of aspects that compare and contrast with each other. And we'll outline all of those things in this table here. Okay, so for example, the first one is definition. How do we define endothermic versus exothermic? Endothermic is a reaction where heat is absorbed from the surroundings. What we have to remember here is the system versus the surroundings. The system is the chemical reaction itself. Everything that's not involved in the chemical reaction is the surroundings. So if you mix solutions together, the water that the reaction is happening is part of the surroundings. It is not actually reacting. The water is just the environment in which it's reacting. So that's the surroundings. And we'll talk about how that reflects in temperature a little bit later. But even, the water could be giving energy to the reaction for it to occur, which is how the system would absorb energy from it. And conversely, the exothermic heat is lost to the surroundings, meaning that the reaction is releasing heat in its throughout its chemical reaction, and the surroundings are absorbing it. Okay. If we were to observe this as a temperature change, what you need to understand is this. Whenever you measure temperature, it's always of the surroundings. You cannot physically measure the temperature of the system. So when I talk about temperature change, I'm talking about the surroundings of the system. So in an endothermic process, the temperature decreases because the surroundings are losing heat to the system. So therefore, the temperature or the energy around the system is decreasing, which reflects temperature, because temperature reflects how fast the particles are moving. And in exothermic, the temperature increases because now you're releasing energy to the surroundings, and the surroundings are what you're measuring. So therefore, the appearance will be that temperature will increase. Okay. It's like if you hold an ice cube in your hand. Okay, if you hold an ice cube in your hand, and the ice cube is the system, your hand feels cold. Your hand feels cold because the ice cube is absorbing heat from your hand, and your hand is part of the surroundings, and you feel that surroundings. The ice cube itself is getting actually warmer by absorbing the heat from your hands. That's the kind of system that we're talking about here. So when you think about temperature, your hand is kind of measuring the temperature of the surroundings because it's part of the surroundings. Okay. Questions? Okay. There are a lot of kind of rows here. Okay. Now, okay. Oh, yeah, I know. If you've had me, you've seen a lot of tables. So, okay, thanks. Everyone's a critic. Which one is that I want to do next? The next one we'll do is place in the reaction. Okay, so where would you put the heat value in the reaction if you were to place it within the reaction with the reactants or the products? In an endothermic reaction, the system is absorbing energy. So you would add it on the reactant side, because everything's relative to the reactants. So if your delta H is positive, or if you're absorbing energy from the surroundings, that means your reactants have to absorb energy to cause the reaction to occur. So therefore, the delta H is added to the reactants.
Is it a delta or a?
Delta.
So it's delta
Huh?
plus delta H?
Yes. No, it's A plus delta H. Sorry, A plus delta. Sorry, I was thinking about the wrong one. So if it's an exothermic reaction, now relative to the reactants, you are losing heat. So the reactants give off that heat as an additional product. That's the definition of exothermic. Yes, Camilla.
I don't understand. So for endothermic, the delta H is in the reactants and then exothermic is in the product?
Correct.
Always.
Yes, because here's how you think about it. You know the law of conservation of energy. Energy cannot be created or destroyed. So the amount of energy on the left side and the right side have to be the same. In an endothermic reaction, what you're saying is because the system is absorbing energy from the surroundings, the reactants don't have enough energy to balance out the products. So therefore, you have to add additional energy to make them equal to each other. Hence why you're adding that delta H on the reactant side.
So the energy going in and out is always equal?
Yes. Yes. Yeah, that is a good way to say it. Like Camilla said, the energy in the reactants and the energy in the products has to be equal. Now, the amount of heat energy, that's the difference between those energies that has to occur. That's what the delta H is. But yeah, the way Camilla said it is a good way to think about it. The energy going in and energy going out have to be the same, so you have to balance that energy by adding delta H on one side or the other. Does that clarify, Camilla? Okay, good. No problem. Now, you don't always write it in the reaction, okay? You may write it outside the reaction, because sometimes you're just given a delta H value and you don't put it in the reaction and you need context for it. In the reaction, the context is which side of the reaction's on, but when you take that number out of the reaction, you're just writing it by itself, you have to give it context, and that context is the sign in front of the delta H. And so for endothermic, you write it as a positive delta H because everything's relative to the reactant. So if you take that number out of the reaction and you want to tell someone this is an endothermic reaction by just giving them the value, you would say this is a positive heat, positive enthalpy. And then the person would say, well, it's positive. That means the system needed to add more energy. Therefore, it's endothermic. And if it's exothermic, that's negative delta H because the reactants have excess heat, so they releases that heat, and so therefore you're losing that heat, which is negative delta H. Yes, Marina.
So this is like in reference to like the actual system,
Yes, it's always in reference to the actual system, correct?
but the temperature change is about the system.
Yes. So what you observe is always of the surroundings, but conceptually, like these values are relative to the system. Yeah. Yeah.
Like, when we say, like, for exothermic, when temperature increases, if it's surrounding.
Correct. Yeah. Temperature always measures surroundings. There's never a time that temperature will ever measure these systems. It's impossible to do that. Okay. Yeah. Energy profile. Okay. An energy profile is not a graph in the sense that there's a change in time or change in stuff like that. It's just a conceptual idea that shows you the energy of the reactants and the energy of the products. Okay. And so what you'll see here is something like this. H, and then the x-axis will just be progress. It's not a time thing. It's just a going from the reactants to the products. So don't think of this as like a graph that you read the numbers off of, like going from left to right. It's just two values that you care about. And on both of them, you have that same thing. So H and progress. For an endothermic reaction, like we said earlier, the reactants have less energy than the products. So if you're going to graph it, you would graph the reactants lower than your products. Okay, because the reactants had to gain energy to get to the products, and that difference in energy is your delta H. Sure. The reactants, because they're at a lower energy state, have to gain energy to equal the product's energy. It's kind of like what you were saying before. The energy in has to equal the energy out.
So the products were at the disadvantage, so the energy had to be added to equalize it?
Wait, what do you mean products at a disadvantage?
Like they were lower?
No, the reactants are lower.
So then why are we adding energy to the products?
No. Sorry, that arrow is not energy to the products. That's representing the difference between the two values. Sorry. So like you're going from reactants up to products. That's what I was trying to draw. Let me move that. I see what you're saying. So just to clarify, what I'm saying is this. Is that better, Camilla? Yeah. So I have to add that energy to get to the products. You're right? Okay. Now in exothermic, it's just the opposite. The reactants have too much energy and the products have less energy. So therefore, you release the heat to get to the products. Now in this topic, we don't care about activation energy. We don't care about the hump and stuff like that. All we care about are the start and ending. So don't worry about like the hills that you might have learned in topic 6 and things like that. Right now, we're just talking reactants energy, products energy. Questions about the diagram or anything like that so far? Okay. And based on this diagram, you can say which side has more energy, okay? And so you can say that in the endothermic reaction, that the products have more energy than the reactants because the reactants had to absorb energy to reach that. And the reactants have more energy than the products here. I know a lot of this stuff seems redundant, but I'm trying to give you different context to understand this because there's a lot of different ways you can ask this question. And so I don't want to just say, oh, this is, it's always negative and always positive, because the IB finds different ways to ask the same question. So they might ask you about endothermic versus exothermic in terms of energy profile, or in terms of energy states, or in terms of which one's more stable, which we're going to talk about in a second. Yes, Marina?
Like you're adding the heat to the reactant side.
Correct.
It's like
Yeah, it needs to try to match it. The goal is for them to match each other.
what if they match each other? Like why is one more? We're not to the up and down.
Yeah, wait, sorry. Did that? So the idea is reactants start at a certain level, and wherever the products are for the reaction, if the products are higher, then the reactants have to absorb energy to reach that state to get to the products. But if the products are lower, then the reactants have to release some heat as energy to lower itself down to the state of the products. So it's all about pathway and which way you're going. But the goal is that whatever your energy of your products is, and your products, the energy of the products, that delta H should add to the side that's deficient in energy to balance things out. Yeah. Gain heat, correct. Okay. Now, the energy state does also relate to stability. Okay. What you need to remember is that molecules and atoms and all compounds and things like that seek to be in the lowest energy state possible. So whichever side is lower energy state, that's the more stable side. So in an endothermic reaction, the reactants are more stable because they exist at a lower energy state, which is what all species seek to achieve. And in the exothermic, the products are more stable. Yes, unfortunately, we have a couple more. I guess 2 or 3 sections, but the last section has a few examples and stuff like that you want to think about. So maybe not. We'll see. Okay. Thanks, Chloe.
No, you always say maybe, but it never works.
Okay. All right. The next section, okay, is a relationship of exothermic and endothermic to bond breaking or bond making. Okay. Because the process of a chemical reaction requires you to break bonds and form bonds or make bonds. And so every reaction has an exothermic side and an endothermic side. It's just a matter of those two values together makes the overall reaction exothermic or endothermic. So every reaction breaks some bonds and forms some bonds. But the difference in energy between those two processes is the overall reaction. Okay. And so which one, breaking or making bonds, would require you to put energy into the system? Sammy.
Breaking bonds requires you to do that.
Why?
You
Okay,
have to overcome
you have to overcome the bonding forces that hold the atom together to separate them. Because the reason why atoms bond together is because if they bond, they lower their overall energy state. So if you're going to make them apart and give them more energy, you have to give them each enough energy to be able to be apart. Okay, so we would put bond breaking on the endothermic side and bond making on the exothermic side. So every time you make a bond, it releases energy. This might seem kind of counterintuitive to biology because I think they kind of use the terminology a little bit weird. Like when you talk about ATP and ADP and stuff like that, it's a little confusing. But in chemistry, when you break a bond, you release energy. I'm sorry, when you make a bond, when you make a bond, you release energy. When you break a bond, you have to absorb energy to do that. The last column, oh, sorry, question? You have to absorb energy. Sorry. So when you break a bond, you have to absorb energy because you have to separate the two apart. It's like if you had two magnets that were stuck together like a bond, you would have to put in energy to pull those things apart. Just like chemistry has to happen that way too. If you're going to pull two atoms apart that are attracted to each other, you have to put energy in. If you let those magnets come back together, they release energy when they come together, whether it's sound or force or whatever. There's some type of energy they release when they come back together like that. Okay. The last column or row for this are examples, okay? And this is kind of more important for HL, but you still need to know this for SL. And because in HL, you talk about this in Born-Haber cycle, but in SL, you talk about each of these reactions kind of independently. So these are some small reactions, not like actual chemical reactions, but concepts of different reactions that you might see in here. For example, ionization energy, okay? When you have a species in its gaseous form and you make it lose an electron, and this is first ionization energy, by the way, just this symbol here. So to make an atom lose an electron, you have to make it absorb energy to release that electron. So one example of an endothermic process is ionization energy, okay? Let's see.
Did you have to know how to explain why endothermic is?
No, you just need to know the concept that ionization energy requires you to absorb energy. Yes, Marina.
Oh, sorry.
Oh, stretching. Okay.
Well, why would it require, is it because you're adding an ion?
Well, you're making it into an ion by forcing that atom to lose an electron. So you have to give that atom enough energy that it can give to that electron to make it leave the atom. Yeah. Okay. Also, phase changes, okay? Solid to liquid to gas, okay? Because what you have to think about is when you go from solid to liquid to gas, you're breaking intermolecular forces of attraction to melt and boil. To break those intermolecular forces of attraction, you have to absorb energy. So moving from solid to liquid to gas, you absorb energy to separate the molecules more and more further apart.
So does that mean the opposite would be?
Correct. And now I'm going to put that over in the exothermic. Correct. Yeah. I'm trying to think if there's any other specific ones that I really want to mention here. No, I don't think so. On the exothermic side, a couple of examples: combustion and neutralization reactions are all considered exothermic, okay? Generally exothermic. So on the IB, if they say combustion or neutralization, like acid-base neutralization, you can assume it's exothermic. Not 100% of them are, but for generally speaking, they are. And for the IB, they recognize it that way. So combustion reactions that you're reacting with O2, we'll talk about that a little later, and neutralization acid-base reactions as well. And like Sammy said, going from a gas to a liquid to solid, you have to release that excess energy. The only way particles can slow down is if they release energy to the surroundings so they can slow down themselves. They can cool down and become slower. Yes, Noah.
So delta H of combustion will always be exothermic.
Yes, correct. Delta H of a combustion will always be negative. Correct. Yes, Marissa.
Why is neutralization, exothermic?
The formation of water and the salt generally releases some amount of energy. And so the only time there may be some, like, there's some carbonates that are a little endothermic, but for the IB, they in the bullet point said you need to assume that all neutralization combustions are exothermic. Daphne, question.
Can you explain why neutralization is exothermic?
Oh, yeah, sorry. So yeah, the idea is that an acid and a base are proton donors and acceptors, and so they are seeking out to lose their and accept their hydrogens. And so when the hydrogens get transferred, the formation of the product is actually more stable than the reactant, so it does release energy.
Okay, thank you.
You're welcome. Oh, that's okay. That's fine if it goes to a laptop. Okay. So that's it for the table. Okay. And that's all of endothermic and exothermic in a nutshell.
Oh, sorry, is that the only example for?
Those are the major examples, yeah.
Okay.
I would say combustion, neutralization, and gas going to liquid to solid. And so remember, particles slowing down to solidify and like condense, they have to lose energy so they can slow down. Okay. All right. Questions so far? Okay. Now, the rest of this unit is essentially solving for delta H for SL. Like there's 4 different ways you have to be able to solve for delta H. And we're going to go through each of those and make sure you understand conceptually about that. So this is the rest of essentially topic 5. Okay. 4 ways to solve for delta H. Okay.
So that's the last thing in topic 5.
Well, it is technically the last thing, but it's a very large portion. It's like 75% of the unit, but it's the last idea. Yes. But it breaks up into 4 different subsections. Okay. The first one is calorimetry. Okay. And calorimetry is essentially the measurement of heat exchanged with the surroundings, okay? Usually water for our purposes here. So this is more of a practical measurement that you can do in a lab in high school, is measuring the calorimetry of a reaction. So you might have done that last year when you reacted and you measured the temperature of the water when it changed, when the reaction occurred. And so the temperature of the water would go up or the temperature of the water would go down, okay? And so you're given an equation in the data booklet for this, okay? It is given as Q is equal to MC delta T. And we're going to break down what each of those variables mean, okay? Q is heat, okay? So it's the actual amount of heat that is generated in your specific amount of reaction you're doing. Delta H, I probably should have said the units as well. Delta H is per mole. Whenever you talk about delta H, is per mole of the reaction, whereas Q is just for this specific experiment that you're doing with the amount of reactants that you're using. Sure. Delta H is per mole. So delta H's units are usually kilojoules per mole, whereas Q is more of a specific to your experiment that you're conducting, like right here. Okay. No, this unit is just kilojoules or joules, depending on. Yeah. So it's not per mole, it's just per the amount that you're using in the reaction. Oh yeah, yeah, sure. Sorry. I would say actually in calorimetry, it's probably gonna be joules, and that'll be important. So in calorimetry, we're doing such small samples, it's usually gonna be in joules for ease of measurement. Okay, M is the mass of the water, okay, which is the surroundings, okay, which is gonna be in grams.
So it's always water?
Yes, for our purposes here, it's gonna always be water.
But it works with like other things.
It works with other things as well, yes. But usually when you're doing a chemical reaction that's aqueous, it's going to be in water, so that's what you're going to be measuring. Okay. And I emphasize water because here's the thing, and this is how the IB gets you, is because the IB won't give you the mass of water in the problem. What they're going to give you is the volume of water or the volume of the solution. And the idea is that you have to know that 1 centimeter cubed of water is equal to 1 gram. Because a student that doesn't know what they're doing, they just scan the problem, look for a mass, and they just plug the mass in. But that mass won't be of water. And so that's kind of the IB filtering out students that are just using the data booklet to get the equation and just plugging in numbers without understanding why they're plugging in numbers. So generally, you're given the volume of water, but then you have to convert it to mass. But a student that doesn't know what they're doing just says, oh, that's the only grams of my problem. That must be the grams I use for the equation for mass. Yes, Sammy. I'm sorry? Oh, no, lowercase, it is important, it's lowercase q. Capital Q is reaction quotient, which is in equilibrium. So there is a difference. That's a good question. It is intentionally lowercase q.
There's so much
I don't know what I'm supposed to say to that. Okay. Capital C. Okay. Specific heat capacity. Okay. Specific heat capacity is the energy required to increase 1 gram of substance 1 degree of temperature. Whether it's Celsius or Kelvin, it doesn't matter, because Celsius and Kelvin are the same increments as you go up. 1 degree in Celsius is the same as 1 degree in Kelvin. So it doesn't matter whether it's Celsius or Kelvin in this. Usually I think you write it in Celsius because you're measuring with thermometers that measure in Celsius. So it's usually Celsius here. And heat capacity itself will be in joules per gram degrees Celsius for its units. Units are a huge, oh yes, Cass, sorry. One. So it increases 1 degree. Yeah. Oh, I see where the confusion is there.
So increase the gram of substance.
1 degree, yeah. Sorry, thank you for clarifying. Oh, it says 1 gram of substance, 1 degree in temperature. If like not a slash, it's like that's supposed to be the number 1 and then the degree symbol. The unit. Yes, joules in energy per gram per degree Celsius. Yes, correct. Yes, that's a good point, Maddie. These 3 values are all relative to water in calorimetry or whatever substance you're conducting the experiment in. Not the system, but of that. So if it's alcohol or ethanol, you would do it for ethanol. They'd have to give you those values though. Usually they stick with water because it's very common. T, yes.
When you said in parentheses degrees or Kelvin, because you're underlying degrees, that means you're always supposed to use degrees?
Well, I would say when you do the experiment, you have thermometers that measure in degrees Celsius. So most likely it's going to be in degrees Celsius. Delta T is the temperature change of said water. What you're measuring on the thermometer here, so the unit there will be degrees Celsius or Kelvin. It doesn't really matter. But make sure you take the difference. So it's final temperature minus initial temperature. And that sign will be important. Like if your final temperature is lower than your initial temperature, that means that means the water lost heat, which makes sense because that means the system's absorbing heat. So remember, if you get a negative delta T, that's an endothermic reaction because the system is absorbing heat from the water. If it's positive, that means it's exothermic because the water is absorbing heat from the system. That's why the temperature is getting hotter. I'm not going to write both those. I figure just writing one of them is enough. Sorry, it's a lot of purple, just all in one page. I need to mix it up a little bit. But again, units are really important. Joules, grams, joules per grams degrees Celsius and degrees Celsius. Write all your units out. I can't emphasize that enough, that if you write your units out, you're less likely to make a mistake. Because the IB is going to test your unit application. They might give you the mass in, again, centimeters cubed instead of grams. They might give you temperatures in Kelvin, or they might ask you for the heat in kilojoules instead of joules. And if you don't realize that you're calculating all in joules, then you will get the wrong number by a factor of 1,000. And that's wrong. There's no partial credit for getting it in joules when they ask you for kilojoules. It's all or nothing. And I know, like, short term, it sounds like, oh, I won't forget this. But when you're doing an IB exam and you've got 10 or 20 topics, these little things that you think in unit tests you won't forget, you will forget and you'll make a mistake. And so it's just writing units out will save you a lot of that hassle and less things you have to remember as well. Minimize what you have to memorize. Yes. Yes, I will go through my my folders and stuff like that and upload some stuff. Yes. Yeah, and then Maddie. You go ahead, Chloe, and then Maddie. Yes, correct. Maddie.
Okay, so for everything when we're solving the cube, we're solving for the heat of the reaction, or the heat of the
Surroundings. That's the thing. That's where we're getting to next. That's a good transition. So the idea here is that we have to remind ourselves that this is always Q of the water, because that's what the surroundings are, because we can only measure surroundings. So if that's the Q of the water, that's the opposite of the reaction. RXN is just an abbreviation for reaction. It's just something I picked up when I was in high school. My teachers taught me that. So Q of the water is the opposite sign of the reaction, because whatever the water is doing, the reaction is doing the opposite. Okay. And your delta H of the reaction is equal to Q of the reaction over the moles of reactant. So however many moles of reactant you use for the reaction, that's what you're going to use. And you may want to make a note that it's generally the limiting reactant. So if you're mixing two solutions together, you want to use the limiting reactant for this. Okay. So whatever is the limiting reactant. So if you're mixing two solutions together, you need to figure out which one's the limiting reactant before you divide by the moles. Yes. So probably what would happen, if I was being honest with you, probably what this would be is they give you a solution like chemistry, like a solution reaction. And the first part would be determine the limiting reactant of the reaction. And then part B would be this reaction was measured using calorimetry, calculate the Q of the water. And then C would be calculate the delta H of the water using the information from A and B. So you know the limiting reactant, you'd know the Q of the water, so then you could plug both those two values in here. So it's, again, the IB trying to weave a bunch of different things together to maximize their coverage of the material. Oh no, you're not subtracting. That's equal, Camilla. So whatever the value of your delta Q of the, your Q of the water is, that's the opposite of the heat that the reaction did. Because the Q is the surroundings. So if the Q absorbed 10 joules of energy, that means the system released 10 joules of energy. Yeah, so they're going to always be the opposite signs. So if,
Your iPad's not on.
is it not charging?
Nope. I have my charger. now.
Oh, no, it's my laptop, not my iPad. Sorry, for some reason, when I plug the power in, after I plug this in, it doesn't charge. Okay, now it's going to charge. Yes. Not today, but yes, there will be a session on stoichiometry and stuff like that. And we'll learn all the different ways to do stoichiometry. Sammy.
Can you explain why the Q of H flows is negative?
Yeah, sure. So what you have to think about is this. The reaction is occurring in the water. And whatever the water gets heat, loses or gains heat, it's gaining or losing it from the system. So if you measure that the water gains 10 joules of energy, where did that 10 joules of energy came from? The system. So therefore, if the water added 10 joules of energy, the reactant lost 10 joules of energy, so it's negative 10 joules. It's just the opposite. It's always the opposite. You don't have to multiply by anything. It's just the opposite sign. That's it.
It's not the reaction, it's the reaction.
Reaction, yes, reaction. Oh, no, yes.
So for my like IA, would like water be the outside, like the surrounding?
Yes, that would be your calorimetry. Yes, Marissa.
So these calculations are saying that completely consistent flow system,
Yes.
like no loss to that.
Well, yes, in your calculations, yes.
So they're like not.
You're not losing any heat to the surround, or like heat to the air and stuff like that, yes. You're assuming that. Now, I guess there are no really lab questions in here because that's in paper 3, so yeah, you don't even have to worry about that. Okay. So, but remember that delta H, if you solve for it using this, it'll be joules per mole. So therefore, you may need to convert it to kilojoules based on the question's desire for answer. So you may need to convert it. But again, writing down units will hopefully avoid you from making that mistake of writing the answer in joules when they want it in kilojoules. Because the IB in the question will always state what unit they want the answer in. In fact, if they do that, you don't even have to write the unit on your answer, technically, because whatever number you box, they're assuming that that's in the correct unit. Now, if they don't say a unit in the question, then you have to write the unit because that's part of your answer. But if they tell you like how much enthalpy in kilojoules in the question, then you can just write the number down. Even if you didn't write unit, it'd still be okay. But I would always write the unit. But that is technically, you're not being graded on the unit in those types of questions because they assume that you follow the instructions, just calculate the number that they want. Okay. Yeah, delta H is the reaction, sorry. Yes. Now, there's a math aspect of this, but there's also the conceptual aspect of this. And you're probably wondering like, well, how do you make this a conceptual question? Well, here, let me show you how we do that, okay? Let's say, for example, we have a reaction where we dissolve NaOH into water, okay? So let's say we're just putting solid NaOH into water and it releases heat. So delta H is negative. Okay. So if delta H is negative, what does that tell you? It's exothermic, right? It's releasing heat, so the reaction is all exothermic. Okay. So how do we do this as a conceptual problem? Well, let me give you a scenario. This is kind of I don't know if it's a what the Tron question, but it's definitely an IB question. Let's pretend we have 2 beakers, okay? And let's pretend we put 4 grams of NaOH into both of these beakers, okay? And we let it react. In this case, with 50 grams of water. And in the right one, 100 grams of water. Now, usually it'll probably say centimeters cubed, but in here, I'm not really having you calculate stuff. I'm trying to help you understand the conceptual part of it. Okay? So we have two completely identical systems where you put 4 grams of NaOH into them. One contains 50 grams of water, and one contains 100 grams of water. Okay? So let me ask you this. Okay? What values are the same in these two systems, and what values are different in these two systems? Can anyone give me one value that's the same or different per in?
There's a difference in pressure because there's more liquid.
Let's not. Well, it is a closed system, but liquid pressure doesn't really have a factor. So let's stick with calorimetry here.
And grams of H2.
Okay, grams of H2O is where?
Different.
Different. Okay. So just making sure. So grams of H2O is different. Okay. Nor
I was gonna say, like, this kinds of NaOH.
grams of NaOH is the same. Okay. Those are the two easy ones. Okay. Not to disparage y'all, but those are the ones that are direct. What else though, if you're doing this as a calorimetry, what else is the same and what else is different?
Specific heat capacity is the same.
Okay, Grant, thank you. The specific heat capacity of the system is the same because they're both in water. C is specific heat capacity from the Q equals MC delta T. Okay, so that, because they're both water. Yeah, so the fact that they're both water makes the specific heat capacity the same. Okay, what else is the same or different? Think about this in terms of calorimetry, what we just talked about. What's up?
Mass is different.
Mass of what?
The solutions.
The mass of solutions, which is mass of water. So we'll have that. We have that under different already.
Oh,
Okay.
okay.
So how does that impact your calorimetry experiment? Anything? Oh, Camilla. Okay, interesting. Okay. Energy is something we need to talk about. Now, what are you saying there? You need more energy to heat it up? Okay, you are on the right track. Okay. Now, the tricky part is this. We have the same amount of NaOH, right? Is that going to generate the same amount of energy? Does the amount of water affect how much energy the NaOH produces? Okay. Okay, but let's think about this. What's heating the water? Well, the water is the surroundings. So the reaction's heating it. Is the amount of reactants we have different? Is the amount of reactants we have different here? No. So both reactions should generate the same amount of energy because you have the same amount of NaOH. So this will have the same Q of the water because you have the same NaOH. Maddie? Yeah, it would be different. Okay. Exactly. So the fact that you're producing the same amount of energy, and like Camilla said, the right one requires more energy to increase the temperature. How would the temperature differences compare? Exactly. So we'll call this number 2 and we'll call this number 1. The temperature difference in 1 would be greater than the temperature difference in 2. Because what Maddie said was, well, she knows Q equals MC delta T. Well, Q is the same, and C is the same, and M is different, then T has to be different to counteract that situation. So if M is greater in number 2, the change in temperature has to be lower. Yes, Tene?
Wait, sorry, how did we know that Q was the same?
Oh, because we have the same amount of reactant in both problems. We have 4 grams of NaOH in both systems, which means it can only produce the amount of energy it can have. So 4 grams of NaOH always produces the same amount of energy. Marina.
Well, I really like what makes sense that the temperature changes, you know, later for the system, because it all the water.
Well, okay, so let me ask you this, okay? Let's see, what's the best analogy here? Okay. Wait, let's see. I had a couple ones, but let me just make sure I do this, okay? What do I want to do here? I want to do this. Okay. No. This is important. I think other people have the same question as well. So give me a second to think about the best way to convey this. And so, I'm probably going through analogies right now. I had one that usually works with cars, but let's make sure I'm saying it right to make it make sense. Okay. Let's see. Let's see. Okay. Okay. Let me not go with an analogy here, because let me say this. Okay. Do you agree that the 4 grams of NaOH in both systems will produce the same amount of energy? Okay. And that energy is going all into the water.
Yeah.
Okay. And that water will change temperature based on the amount of energy that's been put in there. Okay. If you only have 50 grams of water in there, that energy goes twice as far in that water than it would in 100 grams of energy, right? So, okay, here's it. Let's pretend this, okay? I have an analogy, okay? Shopping. Shopping's the best analogy here, okay? Let's pretend you have $200 and you want to buy shirts. If a shirt's $50 versus $100, okay, expensive shirts, okay, but a $50 shirt versus a $100 shirt. If you have $200, you can buy 4 $50 shirts versus 2 $100 shirts. That's what energy is in this case. Because you have the same amount of money or energy, and you're distributing it across shirts or grams of water.
So like the first solution would like get warmer?
Yes, it would.
Like there's less of it.
Yes, exactly. So the heat goes further. Your money goes further in that system than the other system.
Heating a big pot of water.
Exactly. Exactly. You got it. Yes, Maddie.
Now I'm thinking about the original H2O.
No, that's G. Oh no. Wait, you mean Q of H2O here?
Yeah.
Yeah, because the Q of the water comes from the grams of NaOH, not the mass of the water. Yeah, but the delta T goes up when the M goes what? Exactly, so they cancel each other out. Yeah, they're inversely related because they're on the same side of the equation. This is the hard conceptual part about it, but this is the part that helps kind of make things come together. But so
because M is massive water.
exactly. So when you think about this, it's Q of the water. That's a really bad Q, sorry. Okay. Okay. Yes. I understand. Okay, Q of the water is equal to M of the water times C times delta T of the water. So if the mass goes down and this is the same, and the C is the same, then this has to go up. They're inversely related. So this is you applying concepts to the equation here. Okay. Yes, Marina.
So if Q wasn't the same, then that would have changed.
Yeah, correct. If Q wasn't the same, you couldn't make that assumption. Exactly.
But would it be like that? Like they would give us like a different NaOH?
Possibly. But They would probably do it. I'll give you another example in a second. This is a big conceptual thing that we're going to talk about. So I will do another example. I had in mind a couple examples. Yes, Noah. Exactly. Yes. And that's where our second example of this will go to. This is a lot of kind of conceptual stuff, but I want you to understand calorimetry and how it works. Okay. Now, because we have the same grams of water, of NaOH, I'm sorry, NaOH, we have the same moles of NaOH. Because the same grams. Okay. So is our delta H going to be different or the same? Is our delta H going to be different or the same? Why same?
Wouldn't it be different
Why?
if we have more, if number one gets more, has a higher content?
Does it have a higher heat content, Tenny? What do we look at our columns here? Does it have higher heat content?
Like, why does it not?
Okay, Marina. What's our delta H compared in both systems? Why? Yeah. And it's kind of a trick question because as long as you have the same reaction, delta H will always be the same. It doesn't matter how much of each you have. The delta H is per mole. So it doesn't matter, like, as long as the reaction is the same, delta H is always the same. So that's kind of a little bit of a trick question. Well, it's kind of a weirdly worded question, yes. So in this scenario, where you change the amounts of water, the temperature changes, but the heat and the Q and the delta H all stay the same because you have the same amount of NaOH in both reactions.
So the temperature, I don't think I understand the change in temperature.
Okay,
Like,
so do you agree that in both systems you're releasing the same amount of heat?
yeah.
Because you have 4 grams of NaOH. The first system only has 50 grams of water to absorb that heat, whereas the second system has 100 grams of water. So that heat goes further in the first system to heat it up than it does in the second system.
But it's the same thing.
I'm sorry?
But it's the same thing.
No, it's not. Like the first beaker will go higher temperature than the second one will. They start at the same temperature, yes. But we're assuming the change in temperature. So this is back to the analogy of the shirts, Penny, because if you have a $50 shirt versus a $100 shirt and you have $200, you could buy 4 shirts versus 2, and that's your temperature analogy right here. The less mass of water you have, the higher the temperature will go when you give it the same amount of energy. I know this is a lot to kind of take in on a Saturday session, but this is the kind of the high level stuff, yeah. Not higher level like in content, but just like okay, just not close. Yeah, we still, yeah, okay. This is method number 1, but, huh? I'm gonna probably guess now that we're at 12:10, probably 1. We'll see how far we can get through, but okay. Now, really quickly, because I want to go into the next one here. So into Hess's law and stuff like that, and Bond enthalpy. Okay. Yeah, this is just another example. Okay, because I really want you to understand and be able to think this through. Okay. Okay. Yeah, this is still calorimetry. But the other ones, there isn't as much conceptual stuff you have to understand about it. Like the other ones go faster. Calorimetry is a big, especially for SL, because there's not a lot of calculations in SL. Calorimetry is a very popular type of question, whether it's multiple choice or short answer. Okay, so let's say we have 1 and 2 here. But now let's change up our values. It's going to be about the same of what we just did. Okay, 4 grams of NaOH. This is what Nora and Marina were asking earlier, versus 8 grams of NaOH here. And let's say we have 50 grams of water and 100 grams of water here. Okay, so different set of scenarios. You have to think about what's the same and what's different here. Okay. What's the same? Oh, let me not do orange. Oops. And what's different? Okay, Chloe. Specific heat capacity of water is still the same, correct. So the C of the water is still the same because it's just water. Okay. What else is the same or different? Both masses of the water are different. Okay. Mass of water is different. Oh, Sammy and then Maddie. Okay, interesting. Why is temperature change in temperature the same? Okay. It is proportional. So Sammy kind of jumped to the end of the concept, was your change in temperature actually ends up being the same here because he figured out that you have twice as much water in the second system, but you also have twice as much reactants. So the temperature actually is the same because you're heating twice as much water with twice as much energy. So it should go up the same amount. Would it be the same? Would, I know, I'm asking you, would Q be the same? I know, I'm asking you back. I want you to think this out, Maddie. So would Q be the same?
Well, you said that delta T was the same.
Yes.
And then you said that the H2O is
Right.
different.
Keep going.
So like in the first example, it was like that, but this like reverse.
Okay, but now apply everything you said, well, that's same and different, to the equation. So mass of the water is the same, or different. Sorry, mass of the water is different, right? Specific heat capacity is the same,
Yeah.
and delta T is the same.
Yeah.
So can Q be the same? No, it can't be.
Okay, but I just said that because you just said that.
Oh.
Just think of it as like you're pretty much using
Okay.
the same reaction twice.
Yeah. Okay. All right. So, Maddie,
Yeah.
think about this in concepts with the values that you're given. You just said the mass is different,
Oh.
specific heat capacity is the same, and temperature change is the same. Okay. Actually, no, let's go back because I think Sammy kind of went too far here. Okay. Okay. Do you see how you have twice as much NaOH here? If you have twice as much NaOH, you're going to produce twice as much heat. Okay. Right? So that also would make the Q of the water different because you have different amounts of reactants here. Well, no. It's the same. There's a difference there. So do you agree that there's twice as much heat being produced here on the right one than the left one? Okay. So there's twice as much heat, but guess what? There's also, right. So if there's twice as much heat and twice as much water in Q equals MC delta T, and C is the same, then T has to be the same too. Because that's the only way they equal each other. So your delta T is the same, your specific heat capacity is the same, and your mass is different. So if your mass is the only thing that's different, then your Q can't be the same when you multiply that. Okay. Questions about that? This I know this is tough to lean into, but this is the kind of understanding it. Yes.
So since there's more NaOH in one of the
Yes.
there's more energy.
Correct. They're releasing more energy.
But then how does it equal to have more energy and it's heating up?
Okay, so it's twice as much energy, but heating up twice as much water. So analogy back to, yeah, it just clicked, didn't it? Yeah, that's a good feeling. Exactly. If you want to go back to the shirt analogy, it's like having twice as much money, but twice as expensive shirts. You can still buy the same number of shirts. Exactly, it's proportional. Yes, Maria.
So if the mass is different, is like the grams of the is different, is the always
Yes. because it's going to release different amounts of energy into the water. Yes. Yeah, if I'd had my preference, I would have had Sammy answer last because he kind of skipped all the stuff in between and went straight to the delta T. Delta T is the kind of last thing that I wanted to talk about here. So yeah, you look at grams of water, NaOH, to get the Q, and then you realize, well, Q is different, but C is the same. But the difference in what Q is the same as the difference in the water. So therefore, delta T ends up being the same according to this equation. Oh, so I guess the way you think about it is this. In reaction two, it's 2 times the Q of the first reaction, right? Because it's double the NaOH. But it's also double the mass of the first reaction, right? It's double the mass of water, Maddie. Sure. So do we agree that the Q of the water is double? So it's 2 times Q1. So it's twice as much heat as the first reaction. No, Q1 is number 1. Because number 2 is 2 times Q1. Like if you're writing it in terms of the first reaction, Q2 is double Q1. Okay. 2m. So it's double the mass. Okay. And so C is the same. So if you want to do it mathematically, you could do it as well, because look at this. When you bring everything over, the 2's cancel out, right? So therefore, the delta T stays the same. Oh, Maddie just wanted it in terms of like, because she was talking about like how we did it here. I was just trying to kind of show here how that worked, but I used coefficients instead of arrows. Okay. Yes, correct. So they'd be exactly the same in this case, because yeah, number 1 would be Q1 is equal to M1C delta T, and that's what this equals as well. And delta H would be the same as well, because again, it's always the same per mole. This is kind of the higher level thinking that you need to think about with these kind of stuff. Like I've seen questions like this on multiple choice. And like, this is kind of that level 3 type of question that separates students from a 5 to a 6 or a 6 to a 7. It's these types of questions that just kind of pick away at points and stuff like that. But I think if you understand this concept, then you should be able to understand how to calculate calorimetry no matter what. So that's the goal here. Okay. Questions? I know, no, it's okay. But let's move on to the second way. Wait, there weren't any hands raised, were there? I usually get a notification, but I wasn't. Okay. All right, Hess's law. Yes. Now, here's the good news, okay? Hess's law, actually you can incorporate into all the other ways to calculate delta H in one way or the other. So like if you understand Hess's law, you can actually figure out all the other ways after calorimetry using Hess's law without having to worry too much. But let me show you Hess's law. Hess's law states that the sum of reaction enthalpies is equal to the enthalpy of the overall reaction. Okay. So what Hess's law states is that if you want to find the enthalpy of a reaction and you know enthalpies of other reactions that add up to it, you can calculate the enthalpy of that overall reaction by adding those reactions together. Because enthalpy is what we call a state function, which means that the pathway doesn't matter. All that matters is only start and end matter. It doesn't matter how you get there. The start and the end, as long as they're the same, will be okay. It's kind of like in physics with displacement. Displacement is just the difference between your starting position and your end position. It doesn't matter which direction you took. All that matters is that you got to the end point, and that displacement. Okay. So what that kind of means is that if A yields B, and that's the delta H of A, and then B yields C, and that's the delta H of B, what that tells you is that if you add these reactions together, A yields C because the B's cancel out. Because substances on opposite sides of the reaction can cancel out or simplify. If they're the same amount, they just cancel out. If they're different amounts, then you simplify it. Remember balancing half reactions we did in oxidation reduction? You don't have to do that here, but just that when you had waters on both sides, you would simplify it. Like if you had 6 waters on one side and 3 waters on one side, you had a net of 3 waters on one side. That's the same concept. The delta H of this reaction would be A plus B. That's what Hess's law states. Yeah. Okay. Yeah. Okay. To each their own, Corinne. To each their own. Now, here's the trick with Hess's law to kind of make it simpler for you. Okay, here's what you need to know about the IB. Okay, 1. Okay. Actually, you know what? Before I do that, let me give you a couple more things to preface as well. Okay, manipulating reactions. Okay, it's important you understand what happens to the reaction when you manipulate it and how it affects delta H, just to make sure before we go on to the ideas and how to shortcut this. Okay. If you have a reaction like A yields B and delta H is equal to, I don't know, negative 200 kilojoules. If you reverse this reaction, what will happen to delta H? It will become positive. Because essentially you're reversing the reaction, so you're reversing where the heat is. If you want to think of it like this, and then becoming this, that's what's happening. That's why the sign changes when you reverse a reaction, because you're reversing the whole thing in heat, everything included. If you double the reaction, then you double the delta H, because you have twice as many moles of reactants and products, so you have twice as much heat. Okay. Sorry, I had a really big cup of coffee this morning, and now I have a caffeine headache. And so I don't really drink coffee, but I don't know. I was at a donut shop, I'm like, that looks good. And so then I got coffee. Big mistake. Okay. Yeah, I was like, if my handwriting gets worse than it already is, you'll know why. No, I'm good for now. Thank you. Okay. Does everyone understand how we manipulate reactions? If you have everything, then it's negative 200 times 1/2. So whatever you do to the coefficients of the reaction, you do the exact same to delta H. It's opposite. It's not the same as equilibrium where you raise it to the exponent. In delta H, it's literally exactly the same that you do for each reaction. Yeah. Oh, it's still on the right side because it's really plus 2 times heat here, and then it's plus 1/2 times heat here. Yes. So you treat heat like a coefficient, like a substance in its own. So if you double the whole reaction, you double the heat. You have the reaction, you have the heat. Okay. Questions? Hopefully some of this is maybe coming back to you. If not, don't tell me. Okay. Oh, chat. Okay, I hope it's not a private chat. Hopefully it's not bad about someone. Oh, thank you, Grant, for the warning. He warned me about coffee. It's like, it's a slippery slope. You're right. Okay. Thank you. Okay. So here's the trick with Hess's law. And this is kind of more of a trick for IB chemistry because, again, the IB is not trying to trick you contrary to belief. They actually set up Hess's law problems fairly easy for you to do. So tips and tricks about Hess's law. Okay, 1, every reaction is used. There is never, they don't give you extraneous reactions in the IB exam that could distract you from the overall thing. That's not what they're trying to do. They're trying to see if you know how to manipulate reactions. So they're not going to give you like 2 or even 1 extra reaction that you don't ever use. All of the reactions are going to be used for one reason or the other. Okay. But 2, state symbols matter. You can't cancel out a solid substance with a liquid substance of that same version. It has to be the same state of matter. Yes. I don't think that's a huge thing in IB, but I've seen that, like sometimes they do a phase change as one of the reactions. So I guess it is possible. Like you might have to change liquid water to gaseous water. Yes. Oh, H2O gas is not the same as liquid. So you can't cancel those out. Yeah. Okay. Okay. 3, each reaction usually has a unique substance to the overall. And I'll explain to you what that means in a second. Okay. So you're given like 3 or 4 reactions and you have to come up with delta H overall. What you'll notice is that each of the smaller reactions has one substance that's only in that reaction and in none of the other reactions, but it's in the overall reaction. So what that tells you is whatever coefficient that substance needs to be in the overall has to be what you do to that reaction. So when you're trying to do a Hess law, look for the substance that's only found in one of the little reactions that's in the overall reaction, because that will help simplify what you have to do math-wise to calculate it. So for example, let's say we have something like this. I do have some Hess's, oh, not that one. Let's say we have something like, let me add this. Okay, hold on a second. Hold on. Okay. Okay. You don't have to write this down. You can copy this down later, but I'm going to show you what I'm talking about. So in this problem, notice you're given 2 reactions and then the overall reaction. What I'm saying here is that if you notice, only the first reaction has PCl3. Let me zoom in a little more. Exactly right, Marina. So you don't have a choice in what you do, and so therefore that'll make things easier for you because it will all work out based on that. So here you see that PCl3 is only in this reaction, only that reaction. So you have to make it match. So what you have to do is you have to flip it and have it. So you have to do -1/2 here, which makes this PCl3 yields P plus 3/2 Cl2, which is -1/2 times -640. And I recommend you rewriting it out because I think it's easier to see that way. Okay. And notice PCl5 is only in the second reaction. And it has to match this. So what do you have to do the second reaction? Have it. Okay. So then this becomes P plus 5/2 Cl2 yields PCl5. And if you do that through the whole thing, you don't even have to actually check your answer because it'll all work out. Like I promise you, it will always work out. So this is 1/2 times -886. Because look, P's cancel. 3/2 Cl2 and 5/2 Cl2 makes 1 Cl2. And that's the overall reaction here. So it'll all work out. You don't need to really check your answer that much here. And then you just add all the values that you calculated up. And that's your overall answer. Okay, so it's at negative 320, or sorry, positive 320, and then 443, or negative 443, excuse me. So that's what, negative 123 kilojoules. Yeah. You will have a calculator as well. Don't forget, this will be on the Dropbox right after this lesson, so I'll sync it up as well. Huh? Oh, yeah. So do y'all see what I'm saying about unique substances now? If you just match all the unique substances and make them match, it'll all settle out. I promise you. Like every single IB question, like I don't like saying absolutes and stuff like that, but this is one of those situations where if you match everything out, you don't even need to check it. It'll work out. But I still like rewriting the problems. I still like rewriting the equations out just so you can visually see. Yes, Mel.
I don't understand my question, but why would you say
Oh, okay. So you see these small reactions here, and we're trying to make this overall reaction here. When I was saying looking for unique things, a unique thing is PCl3 is only in this first reaction. So whatever this is has to match this in this reaction because there's nothing else to add to it. Yes, and then you.
By 1/2.
Exactly.
Okay.
So you don't worry about CL2. It'll all take care of itself.
Right.
If you find all the unique things, everything else will take care of itself.
And if you still find the normal line, so you just do the regular. Oh, no.
It's
1/2 because it's here.
Exactly. That's the unique aspect of it. Questions about that? There's nothing else really about Hess's law there. It's just manipulating reactions and adding them together. That's it. That's what we're going to do now. Yeah. Yes.
When you said state symbol is not
Not to each other. Like when I say state symbols matter, I mean if you're trying to cancel out a substance, they both have to be the same state symbol. So like here, all the P's are solid, so they can cancel out. All the CLs are gases, so they can cancel out. Then you have to have another reaction somewhere in there that allows you to change them. Yeah. So like if you see a liquid and see a solid you're trying to cancel out and you can't, well then there's some other reaction in the problem that's like solid to liquid that you use to get that.
Would they always give you the state symbol?
If you need them, yeah.
So you'll never end up with the same letter different.
Correct, you shouldn't, unless that's part of the overall reaction. Okay. I know it's a lot taken. I'm gonna warn you right now, like topic 5 was like what, like a 2-week topic for me when I taught 11th grade chemistry. So like this is a lot to cover in like 2 hours, but we are kind of hitting the big ideas. Okay. Enthalpy of formation. Okay, here's what's great about enthalpy of formation because it actually is a Hess's law problem. And I hate that teachers say, oh, just memorize its products minus reactants because again, memorizing that, if you memorize it wrong, you'll never know whether you're right or wrong. So here's the way to really think about it, okay? This is number 3. Okay? And this is enthalpy of formation. Yes. Yeah. Okay, enthalpy of formation or delta HF. Okay. Here's what you need to know about enthalpy of formation, okay? It is defined as the energy change when 1 mole of substance is formed from elements in their standard state at standard conditions. Okay. It's a lot of words just to kind of say you're making elements into a compound, but you can only have 1 mole of compound as your product. So you might have fractions here, and that's okay. One more thing, enthalpy of formation of elements is 0. So if you ever have an element in their standard state, the delta HF of it is 0. The IB may not give it to you in the problem. It may not be listed in the data table, in the data booklet, but it's 0. Of just elements at their standard state. Yeah. No, it is. That's the standard state of that element. Yep. SiO2 gas, that would be 0. O2 gas would be 0. Well, it depends on how you need to balance it. Okay. So for example, if I wanted to write the equation of the enthalpy of formation of water, for example, if I wanted to write the reaction of water, it would look like H2 plus O2 yields H2O. We'll just call it liquid here. But this is gas, and this is gas. And to balance, you can only have one H2O. So like Maddie was saying, you actually have to put a 1/2 O2 here to balance it out. Because the rule is, for this definition, that this has to be 1. Everything else can be fractions, whatever, but this has to be 1. And this will be really helpful for you to kind of understand this with Hess's law as well. Okay. So if I wanted the enthalpy of formation of CO2, what would my reactants be here for CO2? C, and then O2, and coincidentally, it's already balanced. It's already balanced, so you don't need any coefficients. We'll do one more because this is leading to the way to calculate this. CH4. C solid plus 2H2 gas yields CH4 gas. I'll give you a second to write stuff down.
Is that the diagram things that go in a circle?
Kind of. But I don't think you need to think of it in that direction. And you don't need to necessarily see it as an energy cycle, I don't believe. What do you mean? I think probably what you did was you just learned that products minus reactants, you multiplied by coefficients, but you didn't actually look at like how to what it actually meant. I think you just learned that products minus reactants. And using enthalpy of formation. Like to find out the enthalpy of the reaction, you just use products. Yeah. But this is really what's happening behind the scenes here. Marissa. Yes, always 1. Okay. And oh, the definition of enthalpy of formation Camilla says that you make 1 mole of product. So no matter what you do when you're balancing, this has to be 1.
For all of one, one.
Correct. Yes, all these have to be 1.
And also, like what Neil was saying, like what we did with the data book,
That's that. I'm going to show you. Okay. So this is me showing you how this works, because I think it'll be easier to remember this than memorizing products minus reactants and reactants minus products, because it's really easy to get them backwards. And if you just memorize that, you memorize it wrong, you'll never know whether you got it right or wrong. But this way, you, 1, reinforce what the enthalpy of formation reaction is, and 2, you have a logical way to see, okay, I'm thinking about this right, or I'm thinking about this backwards. So I'm going to show you in a second. Yeah, this is where Hess's law comes into play, okay? And this is going to simplify things, I think, for y'all, and be like, oh, that makes sense. I can just do that instead of memorizing products minus reactants. Okay. 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 Yes. Yes, because some of these things, the states of matters do affect the delta H. Yeah. And I wanted to make a match on the examples here because I think that's important here. Okay. The blue is our overall reaction. So let's treat this like a Hess's law problem first before we actually talk about it as an enthalpy of formation reaction. No, this is still the same idea. So we're going to use the green to solve for the blue. because we've already laid out the enthalpy formation of water, the enthalpy formation of CO2, and the enthalpy of formation of CH4, right? We've written what the reactions mean, okay? Okay, so, yeah, let me keep going. So, the data booklet will give you a value for this, give you a value for this, and a value for this. A, B, and C. We're just gonna write that. Okay. Yes, CO2 is G. Yeah. Sorry, yeah, I didn't finish the G there. Okay. Oh yeah. Okay. So, yes. Correct. Huh? Okay. So, Perrin, if you have these three reactions here, how are you going to make that add up to this overall bottom reaction?
Okay, so first I would double the H2O.
Okay, so first thing Perrin says is we need to double the H2O to match this. That's perfectly fine. So 2H2 plus O2 yields 2H2O, which is 2A.
And I would flip C.
Okay, flip C because the CH4 needs to match the CH4 here. So this becomes CH4 gas plus yields, sorry, C solid plus 2H2 gas. And what would our value of our delta H be? Oh, sorry, negative C. Okay.
I would just write B for
B stays the same. So B is just C solid plus O2 gas yields CO2 gas, which is just B.
then I would cancel out the O2. Oh, no.
The O2s add up.
Yeah, the add up.
What cancels out? The C's cancel out.
C's cancel out, and the C.
The H2s cancel out. You don't need to show that, but yeah, you can just add it up. But I was just, in case people were trying to visualize, okay, how does this all cancel out? I was just showing them. No, that was just arbitrary, to be honest with you. She just picked that. She could have done B first and then C second. It didn't matter. But what's the overall delta H for this reaction then? 2A plus B minus C. I'm going to show you in a second. Okay. So, guess what? Oh, yes. Yes, it's solid. So, here's the thing. Okay. Notice all the enthalpy of formations here. Okay. Which enthalpy of formations stay the same? The ones that are where in the overall reaction. Like, which enthalpy of formations stay on the same side? The ones that involve which A and B, which involve which species in this reaction? The products. Which ones do we have to flip? The reactants. That's why it's products minus reactants, not because you were told that way last year. It's because enthalpy of formation, everything you form is in this reaction one way or the other. And the reactants, you always flip. The products always stay the same. So that's why it's products minus reactants. Because 2A plus B is the enthalpy of the products minus the reactants. Yeah. Wait, what's the question? Sure. Okay. So, Camilla, all enthalpy of formations form molecules, right? And those molecules end up in this reaction somewhere. But all these delta H's form these reactants, these products, these molecules. And so if the molecules are on the product side of the reaction, then the sign of these stay the same because they're on the correct side already. But if this molecule that's formed is on the reactant side, it changes sign because you have to flip that reaction. Hence why it's products minus reactants. So wherever the molecule is in the overall reaction, you either flip or keep it the same. Yeah, this is another Hess's law form. They just don't label it Hess's law because they don't always teach you that way that it's just Hess's law. So you could always do enthalpy of formation as just a Hess's law problem. Maddie, yeah, sorry.
So you just make and be together because they're the only ones that stay.
Exactly. So yes, Maddie.
But I don't understand that when you subtract the two, when you do the positive two, because the negative is the value,
No, C is our regular value. C is our initial value.
then
Oh,
what is the
No.
negative C?
wait, what?
What is the blue C?
Oh, this is reversed.
Yeah.
So the negative of C becomes the minus here. So this negative is we're flipping all these reactions, right?
Oh, so when you're doing the formula, you're using the green?
Yes. So that's what you learned last year, that you use the green and you just subtract the reactants. But I think some of y'all may have not understood why that was the case, and this is the case. It's just a Hess's law problem. Marina.
So we don't actually have to do this in the
No.
This is like a proof.
This is kind of a proof, but it's one of those things where you're like, is it products minus reactants or reactants minus products? And if you don't remember,
Why would I not know? Like is there
No.
another thing that's reaction minus?
Yes.
that we could do?
that's the problem.
It's the other way around.
Yeah, that's the problem. If they were all products minus reactants, I wouldn't even worry about this. But there are some that are the other way around. So you have to understand what's actually going here so you don't mix them up. Yeah, I know. So here's how you want to think about it, Marina. If you want to think about it this way, you don't have to write all the enthalpy formations out. This is what I would do. Okay. If I were asked, using enthalpy as a formation, calculate the enthalpy of this reaction, I would pick one of the substances in the reaction, and I'd write out the enthalpy of formation of just that one substance. And then I'd go, okay, the substance in my enthalpy of formation reaction is on my product side. Because it always produces the product, right? So these enthalpy of formations always produce that species. So if I forget, I'm gonna write one of them out, and then I'm gonna ask myself, okay, everything I produce is on this side. Where is that substance in my overall reaction? Yes. So this way I remember that everything is a product that I make an enthalpy of formation, so the products will stay the same sign, and the reactants will be the opposite sign.
So like if I look at it, H2O is, say it was like on the left,
Yes,
then I would be like, oh, so,
I have to flip it.
you have to flip that.
So then that tells you, oh, all the reactants are negative and all the products are all the reactants have to change sign. Yep, that's how you remember it.
But this one, it shows on the right.
Yeah, that's the same thing. Yes.
What if it's on the left?
Well, you'd have to have a whole different reaction. Like, no. So every enthalpy of formation reaction, Marina, has the things you want on the product side.
Right.
Because all the elements are zero. So everything you want in the enthalpy formation is always on the product side. So if you think about enthalpy formations, everything you want is on the product side, and you look at the overall reaction, the reactants have to be flipped, and that's how you remember it's products minus reactants. Does that make sense? Okay. And this is just a way to reinforce it, because yes, there are times where it's reactants minus products, and there's other times it's products minus reactants. And again, I'm just worried with 10 or 20 units of material that you have to remember. One sign is going to determine whether you get 3 or 4 marks right. Yeah, that's stressful. And I want to take that stress away from your memory and take it into your application and your logic. And I think you're better off that way. Yes, Camilla.
My question is that, like when they're asking a question on entropy of formation,
Correct.
they're gonna give you the like what you did, like the delta root, the ability to all that, or are they just gonna tell me what like just the equation and then tell us?
They're going to give you the overall equation and ask you to solve using enthalpies of formation.
Well, how do I know the like I get the overall equation?
Yeah.
But how do I get the like not overall? Like, overall, like, just
Oh,
one on top?
yes. So you pick any substance, and that's your product. And you have to make it from elements. So whatever your substance is in your overall reaction, just pick one, it doesn't matter, and you put it in there as your product. The reactants will always be just elements. So like if I tell you C2H6 as one of my substances, well, the reactions are C, and then H2, and then I just have to balance it.
Oh, so they don't give it to me in that book.
No, they don't tell you the reaction to that, but they just give you the value of it. So that's why I'm saying it's important to understand what that reaction actually is representing in the value.
They just give you, those-
Oh, they'll give you variables.
Yeah,
In multiple choice, they'll give you variables.
yeah, and then you'll have to.
Yeah.
But literally 2x plus.
Yeah, like in multiple choice, because you don't have a calculator, they'll do it in the variable form. But on the short answer, you have a calculator, they'll expect you to calculate it. Yes.
Can you show us what the data book is?
Oh, yeah, sure. So the values here for the data booklet is a whole table that looks like this.
Oh, so they don't, okay. I thought they gave you like the equation.
No, they don't. That's why I said you need note, because that's something they'll ask you. They'll ask you, write the enthalpy of formation reaction for
Okay.
C4H8.
The tables are just every element for itself except for diatomics, which is 1/2, right?
No, because you don't always have to 1/2 it.
Okay.
In CO2, you didn't have to 1/2 it.
That's-
But you're just allowed to have fractions. That's what you want to remember. Okay. Questions? Okay. So yeah, like Camilla said, this is just another Hess's law. If you know the definition of enthalpy of formation, you can treat this just like a Hess's law and not even have to memorize products minus reactants. You could take the time out and write every enthalpy of formation reaction out, and you'd still have plenty of time for the test. You're not going to run out of time on the test. Because this is a 3 or 4 mark question, which means that you have 6 minutes to work this problem. So you have plenty of time to write each enthalpy of reaction, enthalpy of formation reaction, and figure it out on the fly in the problem. You have plenty of time. You're not going to run out of time on the test if you know the process of what you're doing. Okay. Last one, and then that's it for SL. This is the last thing for SL. Okay. Now, but here's the thing. This is also kind of, you could argue this is also Hess's law as well, which is bond enthalpy. Using bond enthalpies.
Is this like a log thing?
Yeah, I don't think it's smush. Okay. Definition of bond enthalpy. Energy required to break 1 mole, just visually to separate the ideas. Wait, no, I changed colors for each. Oh. Okay. I have what we call adult ADHD, okay? And I don't know, I was just kind of kidding there. So I just don't really stay on focus on this sometimes, okay? I didn't pay attention, sorry. 1 mole of bonds in the gaseous state. Okay. So it's the energy required to break 1 mole of bonds in the gaseous state. Yeah. Now, I'm trying to decide on how much I want to do here. There is absolute bond enthalpy where there's only one form of the bond. This is endothermic. Yes, it is endothermic because you have to put energy in to break. So all these values will be positive in your data booklet. And that's important to remember as well. Yeah, only one form of the bond. So like Br2 breaks into B2Br. That's the only time you'll ever see a Br-Br bond. So if I measure the bond enthalpy of that, it'll be exactly the same value for no matter what, because there's only one version. But there are also average bond enthalpies where there are many varieties of the bond. So for example, C to H bond exists in a whole bunch of different molecules and in different energy requirements, because the bigger the molecule, the more complex it is and different energy states it exists in. So scientists don't calculate for every single possible CH bond. That would just be asinine. So what they do is they take one molecule that has just C to H bonds and then breaks them all up and then averages it out. So what they do is they take something like CH4 and break it up into all the atoms. Yes. Okay. And that's the delta H here. Yes, Perrin. Yes, but we don't want any bonds on this side because it's all bond enthalpy. So this is not a formation thing or anything. It's just I want to break every bond and see how much energy it takes. I don't want to form any bonds because that'll affect my values. And what they do is, how many CH bonds do we break here? 4. So we take that value and we divide by 4. And that's our average. Okay. No, you're not really knowing how to calculate and stuff like that. It's just the concept. Yes, that's the kind of challenge here, is that breaking versus forming bonds. And I would suggest every time here that you do draw the structures out and as many as you need to count bonds, because the biggest mistake students make here is they miscount bonds. It's not the fact they look up values wrong, it's they just miscount bonds because they look at a molecular formula and they assume they know how many bonds, and there's actually more bonds than they think. It's all bonds, double bonds, triple bonds, whatever bonds. So like, that's higher level.
I don't understand what you mean by like, a monotone breaking something down.
Oh, okay. Let's just look at this example here, and then we'll go into this. So this combustion reaction here, CH4 plus O2 yields CO2 plus 2H2O. To make those products, all the CH4 bonds have to break, and all the O2 bonds have to break. And then all those atoms have to reform as CO2 and reform as H2O. Yes, and then the net difference is the overall reaction. Exactly, you got it. So let's look at that same reaction in terms of bond enthalpy and how you would tackle that problem. Okay, this, let's say CH4 yields plus 2O2 yields CO2 plus 2H2O. And I'm tackling this as a bond enthalpy problem. Okay. First thing I do is draw everything out and draw the number of them I have out so I can visually. I'm a very visual person. I think writing it on paper prevents mistakes, because keeping things in your mind allows things to be scrambled up. Because you can convince yourself of anything in your mind. Like you can forget a sign as you're going, well, what I'm saying is this, like, okay, sorry. Like, I'm not trying to like manipulate you, but I'm saying like, if you're trying to think out a rationale in your mind, sometimes you start at one point and sometimes you end up at another point and you don't really think about the first thing you had, and so you kind of manipulate things in your mind, and then somehow you get to this reason at the end, which doesn't really make sense overall. Like, it's easy to kind of think about that stuff in your mind and just scramble things. Yeah, logical fallacies, right? So you might think like exothermic reactions are negative delta H, and that might be your starting point, but then somehow you think, well, if it's negative, then it's I'm subtracting from the reactants, and then therefore it's on the sorry, I don't mean to, I shouldn't go further because I don't want to confuse you, but it's easy to scramble things up in your mind. So writing on paper is easier. So here's what I do. Okay. I write out every single bond that's present and number of them as well. So there's two O2s. O2 is a double bond O. Yes, we will go over Lewis structures another time. CO2 and an H2O. Visually, that's super important. Again, because I think a lot of students make a mistake that they see CO2 and like, oh, there's a C double bond O, so therefore, whatever number of CO2s, that's how many CO double bonds I have. No, you actually have twice as many C double bond O's as CO2s you have. And if you don't draw it out, you mess up that coefficient, and then all your numbers are wrong. So yes, you use your data book here. So once you draw it out, you want to tell yourself, okay, how many bonds of each I have? I have 4 C to H bonds, 2 O double bond O's, 2 C double bond O's, and 4 H single bond O's. So I count up all my bonds. I look at what I've written, and I just count up how many bonds I have. But each bond is its own value. Yeah. So that's important thing of drawing it out, right? Every CH4 has 4 CH bonds. Yes, Corinne.
Wouldn't it be 4 O to O?
No, because O to O double bond has a different value than O to O single bond. Yeah. So when you go to your data booklet here and you look at these values, you'll see all the single bonds in the table and all the double bonds down here. Triple and resonance are all in here at the bottom, the multiple bonds as well. So you would look up the values here and you go, okay, CH bond is 414. It's a cross table, so you just draw two lines and find out where they intersect. So C to H is 414. Okay. O to O double bond is down here, which is 498. C double bond O is 804. And then OH is 463. So I'm going to write those down here. So 4 times 414 plus 2 times, what is it, 804? Oh, let me double check. My memory is, okay. And then, no, it's 498. See, this is what I was worried about. This is 498. And this is 804. And this is 4 times 463. So this side is what? 1656 plus 996. Yeah, I mean, yeah, 2,552. 600. I carried the wrong. I carried the one wrong. Sorry. And then 1608 plus, let's see, 1832. Yeah, 1832, right? So that's 3440. Wait, what? 60. Oh, did I carry the number wrong? Okay. No, it's okay. 1, 4. Oh, that's 5 carrier 2. Oh yeah, 1852. So you have delta H's on the left and delta H's on the right. Okay. But like Camilla said before, all the bonds you break are on the left because you have to break all the reactant bonds. Okay. And all the ones you form are on the right. Okay. So what sign will the delta H be on the left? If you break bonds, Marina? Positive. And when you form bonds, you release energy, so the right ones will be negative. So the overall value here is 2,652 minus 3,460. Okay. Someone want to calculate that for me? Negative 808. Okay. So the reactants are positive because you're breaking bonds. The products are negative because you're releasing, you're breaking bonds, or you're making bonds, so you're releasing energy. Okay. But you may have learned this last year as reactants minus products. But that's why it's reactants minus products, because reactants are breaking bonds and products are making bonds, so it's releasing energy. Yep. That's the whole thing. That's why we spent so much time on calorimetry. Yeah. Calorimetry kind of sucks, I'm not gonna lie. I forget I'm still recording. I'm probably not saying anything I should be saying. But yeah, really Hess's law, like enthalpy of formation, bond enthalpy, Hess's law, they're all Hess's laws. That's how you should present it. Okay. Yes.
I understand that like breaking is positive and that's negative, but I don't understand how that has to do with the reaction.
Oh, because instead of putting the sign here and adding these two values together, some people just add up both values and then just subtract them because the products are going to be negative here. That's why you got that. Okay. That's the end of SL. Let's take a 10-minute break and then we'll do HL for the last 45 minutes. Okay, I'm going to pause recording right now. Okay, so higher level incorporates a couple of more forms of enthalpy that you need to understand. And so one is enthalpy of solution. Okay. Okay. And enthalpy of solution is the energy change when 1 mole of solid, is dissolved into a solution. Okay. So it's the energy change when you dissolve 1 mole of solid into a water to make a solution. Okay. This is delta H SOLN, I think the IB writes it as solution abbreviated. Okay. And there's another one as well, which is enthalpy of hydration. Okay. Which is, actually there's three now that I think about it. Okay. The energy change when gaseous ions become aqueous ions. Okay. I guess I should write a reaction for each of these. Sorry, let me write that. I'll kind of squeeze it in here. So enthalpy of solution might look like this. Oh, sorry. What? Yeah. So NaCl solid to NaCl, or actually, let me, into Na plus aqueous plus Cl minus aqueous. Yes, they all have equations. So that first one is an example of enthalpy of solution. This second example would be something like Na plus gas yields Na plus aqueous. And the big enthalpy that is reserved for HL is lattice enthalpy. Okay, bad memories, I know. Okay. Okay. Lattice enthalpy is the energy change when 1 mole of solid ionic lattice is broken into gaseous ions. So it looks something like this. NaCl solid yields Na plus gas plus Cl minus gas. Now, sorry. Oh, enthalpy of hydration is solid. Oh, sorry. Oh no, gas. Sorry, gas to aqueous. And then.
No, it was like the delta H, and then what's the subscript?
Oh, sorry. Oh, yeah. This is delta H, I think HYD. And then this is just delta H LE, I believe. Maybe it's LAT or L. Let me see what the IB in the data booklet says here. So it's. Oh, they call it delta H lattice. Sorry. And they call it SOL. Oh, they call it SOL. And then HYD. It is hydration. HYD. Okay. So this is HYD. This is SOL. And this is lattice. It can be any compound written in that similar form. Yeah, it's just one example. Okay. Oh, just any ionic compound. Like it could be MgCl2 and you can make Mg2 plus and 2Cl minus ions, just whatever ionic compound you want. Okay. This is just another Hess's law. I'm going to be honest with you. This is another Hess's law problem, but they show it in a slightly different way in HL called an energy cycle. And so what this really boils down to is this. The idea is that the enthalpy solution of a system, oops, about 3 or 4 lines, not much. Okay. This is the enthalpy of solution. Is the sum of the following things: your lattice enthalpy, because that's your solid that you start with, and your enthalpies of hydration, because you can convert each Na plus gas into Na plus aqueous, and Cl minus gas to Cl minus aqueous. No, the water is not involved in the reaction, it's just the environment. So these add up to this. So it's just another Hess's law problem, to be honest with you. If you know what an enthalpy of hydration reaction looks like, and you know what a lattice enthalpy reaction looks like, and you know what an enthalpy of solution reaction looks like, which yes, you do need to know, you can generate the sum anyway using Hess's law. And all these values are in your data booklet. Yes, correct. Because everything cancels out and you're left with enthalpy of solution. Now, I showed you that way to reinforce Hess's law, but the IB likes to do this in energy cycles. And so what you may see it as is something like this. This is called an energy cycle. It's just a visualization of the same concept of Hess's law, but the IB likes doing this because it looks similar to the Born-Haber cycle. So they're trying to justify an additional use of energy cycles. So what this says is that these vectors, these reactions add up to this reaction overall. That's all it's saying. So this is an example of an energy cycle showing that the sum of these 3 arrows equals this single arrow on the top. If for some reason one of these arrows was flipped around, you would need to switch it to make it match this idea. So like if for some reason the arrow for lattice enthalpy was going the other way, whatever that value is given, you'd have to reverse it so that the arrow is going the correct way for this reaction. So it's just showing kind of sum of reactions. It's just Hess's law again, just a different visualization. A little bit, yes. That's one form of it, yes. The other one is the bigger one, which is the Born-Haber cycle, which we're going to go into next. Because you'll need to understand all the different reactions that go into Born-Haber cycle. But it's not as bad as it seems to be when we walk through it. Yes. Okay. Born-Haber cycle, okay?
Did you see it last year? Because it was a worksheet to do, and we had like a page full of them.
Yeah, I saw it.
It was like, what was it? It was like a puzzle.
Yeah.
It was actually funny to do.
None of us figured it.
I didn't do it. I just got
Okay.
it off you. That was difficult.
Still on the record, Corinne. Okay. Not editing that out.
Here I do, here I do. Let's be real here. Mr. S had an
Yeah.
absolute.
Okay. Born-Haber cycle. Here's what the Born-Haber cycle boils down to. And I'm gonna switch to the next page so y'all can see. I guess I'll move this down as well. Okay. Here's all the Born-Haber cycle is in the two main reactions, and then you could figure out the rest of them. So the Born-Haber cycle is the dependency of two reactions here. One, a lot. So I would say, yeah, you might want to wait till I draw this out. I'll be honest with you, because if you're not able to follow along, you may not conceive how much energy, how much lines it takes. Okay. No, not that much. Maybe half a page. Okay, yeah, I would maybe wait though. Okay, this reaction here, Na solid plus 1/2 Cl2 gas yields NaCl solid. That looks very familiar based on SL. What type of reaction is that? Formation. It is enthalpy of formation. So this is enthalpy of formation, this arrow right here. Okay. The other big arrow that we are concerned with is this. Na plus gas plus Cl minus gas going to solid. Lattice enthalpy. Now, but it's the opposite direction, right? So this is negative lattice enthalpy because the arrow is going in the opposite direction of what the definition of lattice enthalpy is. Because lattice enthalpy is going from solid to gas, and this is gas to solid. Is everyone following? So the definition, like the value that you get in your data booklet, is lattice enthalpy of going from solid to gaseous ions. But in the Born-Haber cycle, Alexandra, it goes from gas to solid. Alexandra, you with me? So in this diagram, it's going from gas to solid. But in the values that are given in the data booklet, it's going from solid to gas. That's why we have to make the negative of it. We're reversing the reaction. Okay. So everything else in this Born-Haber cycle are just steps to get to this value so that you can use lattice enthalpy. So everything you do to start with at the bottom here is a reaction that allows you to creep toward Na plus gas plus Cl minus gas. And so that's what we're going to outline first. Yes, Chloe. Wait, what do you mean?
Like our Born-Haber cycle is like one singular interaction.
And you flip the arrow and not the negative.
I like doing it. Well, no. Because I draw the arrows so that it looks like the net value is actually expressed of vectors. And so this does, I think this is the way it's going to be on the IB exam. Okay. So, but you are right. If you want to think about it, it all goes in one. If you could draw a full arrow, a singular arrow at the end, and I'll show you that.
I think what we have to do is we have to find the values within the cycle.
Yeah.
So we would have to find like the net and then find the subtraction.
Well,
That's what has to
I'll
go
show you how that works. Okay. But I think starting off with a straight Born-Haber cycle first is what helps you with that. Okay. The first thing we have to do. Na solid. What do we have to convert Na solid to? Gas. The first thing we have to do is convert it to a gas. Because we have to get in gaseous ion form, so the first thing we have to do is convert it to a gas. This is called atomization, where you convert a solid metal, into a gaseous atom. Okay. Now that you have a gaseous state, what can you do to the Na? Ion. Okay. You can convert that Na to an ion. Okay. What do we call that? Ionization energy. It's going to be first. Yeah. If it's a second, it'd be Na plus to Na2 plus. Yes. Those would be two separate values that you'd add together. So if it was like a group 2 metal, you'd have to do both ionization energies, first and second, added together. Okay. So now we've already got Na plus, right? So this is, let me finish actually writing this out because I think that's important here. So 1/2 Cl2 gas, and then, so we're just changing the Na. Okay. Yeah, there's gonna be a couple more things. Well, yeah, 2. What do we have to do to the Cl2 to try to get it to become Cl minus gas? Well, we have to make it Cl and we have to gain an electron, but we have to make it Cl first. Okay, so what are we doing when we're converting Cl2 into 2Cl? What are we doing chemically? If we convert Cl2, breaking bonds, exactly. Okay, so what do we call that? What's that measurement called? Bond enthalpy. So this is bond enthalpy here. Okay, so this becomes Na plus gas plus Cl gas. But what does bond enthalpy represent? How much Cl2 does bond enthalpy represent? 1 mole of bonds. Are you breaking 1 mole of bonds here? Which one are you doing? Half a mole of bonds. You do 1/2 here. Because it's half a mole of Cl2. So there's only half the mole of bonds you're actually breaking, so you have to have the bond enthalpy.
So like this, that's
No, no. It's the coefficients that matter. Okay. And lastly, going from Cl to Cl minus is gaining an electron, which is electron affinity. Okay. Which is plus electron yields Cl minus gas. Now, I draw the electron affinity arrow as a curly arrow because sometimes it's positive, sometimes it's negative, but it doesn't matter. That's the right direction in which you're doing it. Okay.
So you went with the first step, which you have the NaCl, and the first step you did the
Na.
Na. So you went like that way. That one was the first arrow then, with the delta H.
Oh, that's the end. So this is the start, and this is the end. So what you could say is either you go from the start to the end, or you go around this way, and it's the same difference.
So in the question, they're going to give you, like, what are they, what's like the first given?
It just depends. If they want you to solve for enthalpy of formation, then they'll give you values for the other parts, and you'll have to put it all together to solve for enthalpy of formation. But they could give you enthalpy of formation and have you solve for something else within the Born-Haber cycle.
Oh, okay.
So this is why what Chloe was asking earlier is that if you want to solve for different parts of the Born-Haber cycle, this is what you do. You find your start and you find your end point and draw an arrow from your start to end, and then change all the arrows to match that. So yes, Camilla.
My question is that, is each step that you have to like a different step, but like it was like, I mean, you're doing something.
Yeah, those are all the names I wrote next to the arrows.
Oh.
Yeah.
And like, and you have to know which one you do.
Yes.
In order, like in order, like, the order that. But you never have to worry about all that.
You won't ever have to write it or draw it, but you might have to label it. Like they could give you a blank one, or like ones that are missing the labels for each type of reaction and ask you to label those. So,
Yeah, can you figure that out though?
well, I guess it depends on if they actually write the products in there. They could leave that blank and go, what are the like things that belong in this thing? So I would still be careful about it.
I'm just like, because I remember last year, like, wasn't the start the NaCl and then you end with NaCl?
No, enthalpy of formation reaction this direction is always that. I think what you're thinking about is if you use the Born-Haber cycle to solve for lattice enthalpy. Okay. So this is what I'm saying here. Let's say the start, the end is not here and here. Let's say we want to solve for lattice enthalpy. Okay. Well, then this would be the start and this would be the end, right? So you draw the arrow going this way, correct? Yeah. So this brown arrow is the same as the blue arrow, net-wise. So what I would do is I would flip the enthalpy of formation, because the arrow is going the wrong way, add atomization, add ionization energy, add 1/2 bond enthalpy, add electron affinity, and all of that would equal my lattice enthalpy. Do you see how I did that? When you're thinking about last year, all I'm saying is when you think about last year with Born-Haber, you're being taught how to calculate lattice enthalpy. Right. So now, if there are other situations where you might have might be trying to solve something different, using this whole thing will help you do that. Okay. Because for example, if you wanted to solve for I don't know, bond enthalpy, then that's here all the way to here, right? Because you'd be solving for this arrow right here. So you'd flip all these arrows that were going the wrong direction, add them all up, and that would equal that overall arrow in the middle there. And so that's why I think writing it this way with the arrows in this direction is important, because it allows you to solve for any missing spot in there, because you can just draw the arrow from start to finish to direct you on what you need to change signs for. But you just have to remember that because your lattice enthalpy arrow is going down, that it's the negative value of lattice enthalpy. Yeah, a lot of that stuff comes from the periodic trends chapter, but yes, you do need to know these reactions. I would just memorize the definition and you can come up with the reaction from the definition. Yes, Alexander. I guess sometimes they call it atomization there as well, and then they just have the value for you already. You will use bond enthalpy because that's what's given in the data booklet. So I would get used to doing 1/2 bond enthalpy here. That's only because there's a 1/2 in front of the Cl2. Then that's just regular bond enthalpy. Because you multiply bond enthalpy by the coefficient there. The coefficients translate throughout. So if you have two NAs, you double the ionization energy, you double the atomization as well. Daphne.
So for lattice enthalpy, you're going from solid to gas. But
Yes.
for formation, is there no rule in terms of states of matter? Because you're doing
No, it is always just standard states for each substance. So there's no gas to solid or solid to gas or none of that. It's just the standard state of each substance.
Okay, thank you.
Yeah. So you just need to know the direction of the arrow is pointing toward the 1 mole of product away from the elements. That's the way you want to think about that.
Okay.
Okay. That's the Born-Haber cycle. Okay. We'll revisit that again, but we got to kind of move on. Okay. Okay. Entropy, really quickly, okay, is the measurement of, oops, I skipped ahead, of disorder in a system. It is notated by capital S. Okay. And every system has disorder. Every system, because if the only way you have no disorder is if you're at absolute zero, and every system is above absolute zero. So the S value is always greater than 0 for everything. It's always positive. What isn't positive is the change in entropy, which is from reactants to products. So the change in entropy can be positive or negative, just like enthalpy. Okay. And you treat entropy like you do enthalpy of formation when calculating. So it is going to be products minus reactants here, just like enthalpy of formation. So if you have to calculate entropy, the change in entropy, it's like the formation using entropy, and so you end up doing products minus reactants. The only catch is delta S is usually in joules per mole per Kelvin. So the units are the big kind of trick here, that it's a much smaller value than enthalpy. And so your values are going to be in joules per mole Kelvin, and that'll matter in Gibbs free energy. They do already. Yes. So the units, if you go up to this table here, they are nice enough to give you the units for all those. So there's no reason why you shouldn't get them right, but students still don't. So you have to really be careful about that. Okay. Now, sometimes you might have to calculate, but a lot of times entropy is just about conceptual stuff. So like being able to predict whether it's positive or whether it's negative, not in actual value, but just kind of saying, oh, in this scenario, it's positive, in this scenario, it's negative. And so for a positive delta S, which means you're increasing disorder, examples might be like this. Increasing temperature, because the faster particles are moving, the more chaos and the more disorder is present. Going from solid to liquid to gas. Again, the more movement particles have, the more probability and the more kind of randomness of locations that can be, not probability, but randomness of the order of the particles. So going from a solid to liquid to gas is increasing disorder. So the sign of delta S should always be positive. Going from a solid to aqueous, when you dissolve something, you are making more disorder by separating the particles apart. There is one thing with pressure, and that has to do with gases. And so when you have moles of gases, it matters. And so when you have more product gases than reactant gases, that's an increase in entropy as well. So if you see something like this, NH3 gas going to N2 gas plus 3H2 gas, that's 4 moles of gas and 2 moles of gas. So this should have a positive entropy. The difference in moles of gas doesn't affect the actual entropy. It's just 4 is greater than 2, so you have more products, so you're getting more disorder. The more gas molecules you have, the more disorder that's possible. Right. Oh, because a positive delta S means that the reactants are becoming more disordered when they go to their products. So there's more chaos that's increasing. So like when a solid goes to a liquid, there's more disorder, right? Because the particles are moving around more freely, so there's more disorder. So if I tell you I'm melting an ice cube into water, what you need to understand there is that the delta S will be positive. The change in entropy will be positive. Correct. That's the idea of this. So these are a list of, no, go ahead. Well, getting more ordered. A liquid could be positive or negative depending on where it came from, right? Exactly. If a liquid goes to a solid, it's a negative entropy. But if a liquid goes to a gas, it's a positive entropy. So everything I listed here, the opposite is negative. The gas mole thing is big. Like I would say that's the biggest one that they talk about. They give you a reaction and say, what's the sign of delta S? You just look at only gas moles. So make sure you underline that. And when you explain your reasoning, it's only the gas moles that matter. Not solid, not liquid. It's just gas moles contribute to disorder. The most, I should say. Correct. The more, Yeah. Yes, Chloe.
We're doing, are you guys doing ionization and fluidicity on that?
Probably in topic 3, where periodicity happens. I might have actually inadvertently mentioned it in topic 5 when we were talking the examples. I think I did kind of mention the reaction at least. Okay. So that's delta S. Okay. Now, that's what we're getting to. Gibbs free energy. Okay. Delta G is Gibbs free energy, or the change in Gibbs free energy, I should say. Okay. So this is the energy available to do work in a reaction, meaning that as a reaction occurs, is it providing more energy that the reaction can consume and continue on, or is it in constant need of more and more energy to progress forward? Okay, and that's the idea of spontaneity. Okay, is the reaction self-sufficient in energy, or does it need a constant supply externally for that? No, this is a whole separate thing. Sorry, I should draw a line. It is related to entropy, which we'll see in a second. Okay. Now, if you have negative free energy, that means your system is releasing energy that you can use to perpetuate the reaction. So you want delta G to be negative for spontaneous. Yes, the system is producing energy in one form or another, whether it's heat or potential energy, one of those ways, so that the reaction can continue on its own. Oh, change. Sorry, yeah, I wrote a delta symbol there, so I wanted you to make sure that you understood it was the change in Gibbs free energy. Because the reactants have free energy and the products have free energy. But again, it's the difference between those two that matters. Yes, Camilla. To proceed the chemical reaction, to continue the chemical reaction.
So if something is spontaneous, it keeps going?
Until it runs out, yes.
And what if it's not spontaneous, if there's like a limit to that?
No, that it will not go on its own. Like, for example, an ice cube, an ice cube, if you put it out on a table at room temperature, it's going to melt spontaneously because there's enough heat around it just naturally that it'll melt. But if you put an ice cube in a freezer, there's not enough heat around it for it to melt on its own. So that would be non-spontaneous. So there's not enough conditions. Exactly. Wait, what? Well, it's just the opposite. So non-spontaneous would be delta G greater than 0. There's 2. Yeah, which we're going to talk about next. Okay. Greater than 0. 0 is included in spontaneous. Okay. Now, so what Marissa talked about is the next part of this and how to calculate delta G. Okay. Now, you can do delta G using formations just like delta H formations, like we talked about earlier. So you can do it like that, but that's not the way they're usually going to have you do it. What they'll do is they'll expect you to use this equation. And this is given to you in data booklet, so you don't have to memorize it. Yes. Delta GF you can treat like delta HF, even in the fact that delta G of elements is 0 as well. I guess I should jot that down. Delta G of formation of elements is equal to 0, just like delta H. But entropy is never 0. Okay. This is the big delta G equation. Okay, this is the big one for topic 15 that you have to understand and know. You don't have to memorize it because, like I said, it's in the data booklet, but I would still know it because maybe on the multiple choice they might ask you something about it. No, you get no calculator or data booklet. All you get is a periodic table. I know. That's kind of where they take the opportunity to ask things that are in the data booklet is in the multiple choice where, so like when I say you don't need to know because it's in the data booklet, I would still be aware of it. I wouldn't like stress out about memorizing it, but as you study the data booklet, I think inherently you'll remember some of the stuff that you may need to know. And we'll talk about that when you get to know your data booklet. Okay, so let's break this down. Delta G is Gibbs free energy. And the unit of that is kilojoules per mole. Huh? It is not. That's delta S. Delta H is enthalpy, which is kilojoules per mole. Delta S is entropy, which is joules per mole per Kelvin. And T, which I forgot to write in that order, is temperature in Kelvin. A.
Okay.
That's fine. Entropy is with an O. Okay. This is one of those things where units really matter because, again, this is one of those cases where the IB is very smart about what they give you in the data booklet and what they don't give you. The IB doesn't tell you any of these units in the equation that they give you because they want students to still know and understand how to use this and write your units out. And so the biggest mistake students make here is they just don't follow their units and they start combining stuff together. They forget that entropy is in joules per mole and everything else is in kilojoules per mole. So you can't subtract delta H minus T delta S because they're different units. So what you generally have to do is divide this value by 1,000 to convert it into kilojoules. And that's the biggest mistake. Yes, Pern? Oh, stretching? Okay. So that's the biggest mistake students make is they forget to convert because they don't write their units down. They just plug numbers in blindly into an equation and then they forget and then their number is completely off. Yes, Pern?
So in the equation, you need to convert it to kilojoules?
Yes. I would say 99.5% of the time the IB gives it to you in joules to make sure you convert units. There might be some random time where they give you delta S in kilojoules, so pay attention to the units, but the majority of the time they put it in joules to make sure that no one, again, the IB is all about not giving a student that doesn't know what they're doing a chance to get the question right. They don't want you to stumble into the right answer. They want to make sure you earned it, so they're going to put every kind of quote unquote obstacle in the way from someone just being able to show up and go putting numbers in an equation, getting it right. They're going to set up those barricades. Not trick you. They're trying to reward the kids that know what they're doing and punish the kids that don't. Whatever category you fall into, I'm not going to tell you. I think you know. Yes, because there are 1,000 joules in a kilojoule. Yeah. Will we finish in the next 5 minutes? Yeah. Well, I would probably spend more time on it, but this is fine. Okay. So the conceptual part about this is the last thing I want to talk about. Okay. Because sometimes you don't actually have to put numbers in, you just have to be able to understand signs. Okay. And understanding what signs you could get or you couldn't get based on the signs of delta H and of delta S. And so this is the conceptual part. Okay. So what we're going to do is this. We're going to create a table, not a big one. Delta H minus T delta S. No, you don't need a lot of space for this. 4 lines is probably sufficient. Okay. Yeah, that's fine. Okay. Now, what are the possible signs of delta H? Positive or negative. Okay. So this could be positive or negative. What are the possible signs of delta S? Don't overthink it. Positive or negative. So how many different combinations of H and S could you have? 4. You could have negative delta H, and positive delta S, and negative delta S. and you could have positive delta H, positive delta H. I'm going to talk about that in a second. Because delta S has two possibilities. I'm doing all the different possibilities.
There's no words in this one.
Correct, there's no words. Okay. And I'm going to write negative T in here afterwards, because I want you to think about that separately. Well, we're going to talk about it in a second.
Oh, it's just like the minus.
Yes, it's the minus sign. Okay. So each of these possibility signs can get you different possible delta G's. Okay, based on this combination. Okay, so let's look at this first combination here: negative delta H and positive delta S. Okay, what happens to our positive delta S when multiplied by T? Becomes negative. So it's a negative plus a negative. So it'll always be negative.
Oh, it's not times.
Right, it's not times. It's adding. So when you have a negative delta H and a positive delta S, it is always negative delta G. Always. There's no way, because temperature is always positive in Kelvin, so it's always spontaneous. Okay. Yeah, and that's what we're going to talk about. Okay. Now, this second one, with a negative delta H and a negative T times negative delta S, that side becomes positive. Okay. So what's the one variable that we actually have control over here? Yes, Prin? Temperature. What kind of temperature would you want so that when you add these terms together, you would get a negative number? Huh? Why?
Because then they would do minus is bigger minus.
It's not a minus. Well, no, because remember, this,
It's a positive.
it's positive.
So still bigger because the minus from a bigger number, so it's still positive. Wait, you want it to be negative?
Hold on. Okay. Prin, I think you're mixing things up. Okay. Let's backtrack, Prin. Okay. T is always positive. It can never be negative. T is always positive, but it's negative T, right? So negative T times negative delta S is a positive number, which is hurting your ability to be negative. But you want a negative number. So you want, yeah, that's not what you said originally. So I'm trying, but it's all recorded, okay? So in the second scenario, because this is a positive, you want a low temperature for it to be spontaneous because temperature is hurting you.
So trying in all of these pieces, we're gonna have a low delta G.
You're trying to have a negative delta G. Correct, Maddie. You're trying to have a negative delta G because that's spontaneous. So we're trying to figure out when it's spontaneous and when it's not spontaneous. Okay. In this third combination, okay, delta H is positive and negative T and times negative S is a positive value as well. So it's a positive plus a positive. So is it ever spontaneous? No. So this is never spontaneous. Because you're going to get a positive delta G always, no matter what. Wait, what? Okay, what that means is if you want a negative delta G value, you have a negative delta H, but minus T times minus delta S is a positive number. So you have to make sure that your negative delta H is greater than your positive T delta S, so that your overall number is negative, right? Because you're adding the two terms together. Wait, what do you mean? Oh, yes, it could be either or. Correct. But it's spontaneous at low temperatures. Because we always ask whether it's spontaneous or not. Well, I'm saying at low temperatures, it's negative delta G.
Oh, okay.
This last term here, you have positive delta H and minus T times delta S. You want a big T because this is negative and so it's helping you out. So you want high temperature to get a negative delta G. Because that term is helping you now instead of hurting you. I don't want you to memorize this table. Okay, that's not the point of this. The point of this was to prove what's going on so that way, anytime you run into the scenario, you can make the line that you need for the problem. Okay, don't memorize this. I'm just showing you that if you got to a situation where you had signs for delta H and delta S, you could figure this line out yourself. Don't memorize. But just to prove that if I know this equation, and I know the sign of delta H and the sign of delta S, I can tell when it's going to be spontaneous. Yeah, you want a negative delta G. Okay. Now, just one disclaimer to finish this up. Low and high temperature is relative to the reaction. So do not assume low just means cold. Low could be 500 Kelvin and high could be 20 Kelvin. It depends on the reaction. So do not assume low means a small Kelvin value. Every reaction is different, and a low might be a very high temperature compared to like average standard temperature. So don't think that just because we say low temperature that it has to be really, really cold. It's all relative to each reaction.
Just have to mean that like whatever that number is times the delta F has to be lower.
Yep, right, Maddie. So in the second row, whatever the temperature is times delta S in kilojoules has to be less than the delta H. Exactly. You got it. Okay. So I don't know if you learned last year, like there was like this like axes where you like always high, never low and stuff like that. Don't worry about that. Just know that if I have the equation, I know the sign of the two things, I can figure it out. I think y'all are capable of that logic. If I'm wrong, then I apologize. But I'm going to assume that you're capable of that logic. Yes. Born-Haber cycle, yeah. Here. Here, just leave it here so you can write it down. Okay. All right. That's the end. It's 2:05. I'm sorry I went a little bit over, but that's it. So I'm going to pause recording now and upload, or I'm going to stop recording.